slower particle will have a smaller curve than the faster particle. So we now know this has happened, and from the deflection to the left we can tell that it's a positively charged particle, and also by looking at the way this is curved we can tell you something about the mass-charge ratio again. So we found that these are the particles that have the same mass as electrons but positively charged. In this article, the positive electron basically is the proof of the first proof of antimatter. So antimatter has always been a very a spooky thing, but antimatter is all around us. These particles, they come out of a banana, basically, for instance. So they are all around us. We never notice them, of course, but because most matter is normal matter, not antimatter, but it has always been there. And a couple of years ago I was at CERN, and they have this building there that looks like this, and that's of course a great name. So if you have this, then you put this on the building because it looks fantastic. Of course there was a book written about that, a very successful film. That was completely ridiculous, but anyway, this is not. This is the antimatter factory at CERN in Geneva, and they do research on antimatter. They even created anti-hydrogen. So with an anti-proton, with an anti-neutron, with an anti-electron. So this is anti-hydrogen, and they do research on that, and they even look if these anti-particles have a different interaction with gravity. They're not falling upwards, that's not the case, but you should look at if they are falling down differently. So far that is not the case, which is good to hear, but also a bit sad, because you really want something special happening, and then perhaps new physics is on the way. So, the second problem were these electrons that were shot out of the atomic nucleus with different velocities. Well, Pauli said, well, perhaps the total energy, of course, is conserved, but the total energy is spread out over two particles, the electron and another neutral particle that we don't see. And that's really awful, because he really didn't like it, that he sort of predicted an invisible neutral particle as a solution to a problem. That's really not a really scientific way of dealing with problems. But basically he called this little neutral particle, he called it the neutrino. And the image then is this. And instead of just a proton and electron, there's also this neutrino, this little neutral particle shot out of the core. And of course you don't easily see that, because how will you catch it, right? Well, this is 1930. It took till 1956, 26 years, before they were able to really see these neutrinos in a very fancy experiment. They use a slightly different reaction, as you can see here, but they basically saw this reaction happening. We have basically it was called Project Poltergeist, by the way, because you're trying to catch this invisible particle moving through your house, well, sort of this. So, and they had this nuclear reactor as a source of neutrinos, very close by. They had this tanks of water with cadmium chloride, really big atoms, and hopefully some of the neutrinos would hit these cadmium chloride molecules, and then out come particles, and you try to catch the particles in these three scintillating layers. It's a special construction that with cameras around it that you can see flashes in, and then hopefully you can reconstruct these tracks and find what reaction has happened here. Now the thing is, this was not the first experiment that they proposed. So basically, if you let physicists think of an experiment, the ideal experiment to find something, then you should be aware, because the first proposal was this. They wanted to dig a shaft 50 meters deep with a tank here, and they hang the detector here. The detector was a big tank of 3 cubic meters of liquid, and before this time these scientists had only worked with 1 liter of this stuff. So now they were talking about 3,000 liters of liquid in the detector, And then basically you, at the moment of measurement, you give a signal that breaks the signal that the sense of an explosive, and this detector starts to fall 25 meters, really on a bed of feathers and foam rubber in this vacuum tank. Now, why do that? Well, I'm going to tell you in a couple of seconds, but this detector was very big, and they called it El Monstro. It was a monstrously big thing, and you drop it 25 meters. The thing is, you need a neutrino source. And of course, a nuclear reactor is a fine source, but a better source is basically an atomic bomb. So they set off an atomic, well, that was a proposal, to set off an atomic bomb. This is 50 meters from this opening, so something like that, it's very close by. An atomic bomb, the same strength as the one that was dropped on Hiroshima in Japan. So obviously you couldn't be next to that. They did all kinds of atomic experiments in those years. And the radiation from this then would have been detected by this detector, but they dropped this detector because if you hang it in this tank and the bomb goes off, everything is shaken to bits. So basically, just before the explosion of the bomb, they dropped this detector. It was in free fall in this vacuum. Everything around around the tank and everything was shaking because of the atomic bomb explosion. But this detector was falling in free fall, and it wasn't shaking because otherwise they couldn't do the measurements. And then it hit the bottom, and of course then they had to wait a couple of days or weeks even for the radiation to die down before they could retrieve the detector at the bottom of this shaft. Of course, if you do this proposal, this is the ideal way. You have an atomic bomb with lots of neutrinos, lots of measurements, great experiment. And then you propose this to your director, and then what does he say? Approved! Yes, let's do this. It was actually approved, this plan. They didn't follow through. They thought, well, perhaps it's too difficult, it's too dangerous also, let's try this thing with the nuclear reactor. And of course they found the neutrinos. But this is an insane thing that you can use atomic bombs to do physics experiments. I thought it was a funny story.